right, we're gonna jump right into it. All right,
For
hello.
0 viewers on Kick and
Okay.
Twitch, I'm sure.
All right, I'm back. All right, sorry about that.
Excellent. And are you live, sir?
Yes, sir. We are live. So we're gonna get into it tonight. We're gonna read a little bit about curved visual space and what that is. We've all been hearing a lot about it, and shortly hereafter, we're gonna hear a lot more about it. So this paper will kind of get into a direct measurement of it. So we're gonna look at that and the differences between the predictions of curved visual space and Euclidean geometry. And to give a quick preface on that, actually, now we'll get into it. We'll discuss the alley stuff later. Let's get into the reading. So this is going to go over a an experiment of measuring curved visual space. So this is direct measurement of the curvature of visual space. Sounds very interesting. I wonder what that means. You guys see that? Okay.
Yeah.
Okay. Cool. All right. So abstract. We consider the horizontal plane at eye height. That is, that all objects seen at the horizon, although this plane visually degenerates into the line of the visual field. The depth dimension, nevertheless, gives a two-dimensional structure. We address the problem of intrinsic curvature of this plane. Classical geometric method is based on Gauss's original definition. The angular excess in a triangle equals the integral curvature over the area of the triangle. Angles were directly measured by a novel method of exocentric pointing. Experiments were performed outside in natural environments under natural viewing conditions. The observers were instructed not to move from a set location and maintain eye height, but were otherwise free to perform eye and head movement and body movements. We measure the angular excess for the equilateral triangles for the sides of 2 to 20 meters, the vantage position at the barycenter. We found the angular excess in deficits of up to 30 degrees. From the data, we constructed the metric. The curvature changes from ecliptic in the near space to hyperbolic in the far space. At very large distances, the plane becomes parabolic. Okay, let me read a message from JT. You can hear me on Space Audits, or you can hear me on Space Audits, but not on. Can you guys hear me on Discord?
Yeah.
Can you guys hear me on the stream, live stream? 1 second. Oh, it's because I'm lagging on stream or whatever.
Terrific.
Yeah, it'll sort itself out. As long as you guys can hear me, it's fine.
Yeah.
Yeah, it'll be fine. Okay. So what we're discussing here is we have, if you if you break our vision up into curved visual space, right? What it would look like. See if I have the diagram prepared. Sure don't. Give me 1 second. We'll just talk about it later. But anyway, basically, you have a near field and a far field, right? And then even further than that far field, there's a different type of optical compression that you experience. So what they're describing here is the different levels of optical compression that you'll see in relation to physical objects in three-dimensional space. So let's say an object of a certain height and is a certain distance away from you. How you will scale that object to fit in your 180-degree field of view will be based on curved visual space, right? And as that object gets further away from you, the proportionality scaling will change to make it fit accordingly. And then especially when you add other objects, like in the background, for example. So if you take a building, right, in your near field, right, a building will appear taller than mountains in the background, right? But we know that the mountains are way taller than the building, but the optical compression rates due to things in the distance versus things in the near field is going to scale proportional so that it all fits, right? So this is this is a description of the mechanism for that, right? So if you break your vision into near field, far field, and then things that are just completely at the horizon, right? All right, introduction.
Yep.
People routinely commit appreciable and typically systematic errors when asked to estimate geometrical positions of their environment from a fixed vantage point. Barato and others, 1967, 1976, 78, and Wagner in 85. This is not surprising in view of the fact that these geometric properties are only implicitly specified by retinal images. Conventionally, one distinguishes between the visual field and the visual world. Prenny, it looks like a French lad there. Toby, you got that one? Your boy Prenny?
Piran?
Prenay? Oh, okay.
Piran?
Yeah. Prenay? It's Prenay, Toby. Okay. 1970. So the geometry of the visual field is that of the simultaneous presence of the variously colored patches. The visual world involves an additional depth dimension. Depth properties are specified by binocular disparities in optical flow, and they are. What's that?
Did we say who this guy was first?
Who's that? The guy
Did we
that
say who this Gauss? Isn't this? Is that
the
what we're
dude?
reading?
No. We're reading a 2000 a paper from 2000 by Jan Codenderker.
Oh,
Kind of whiffed on the last name there, but anyway.
okay, all right.
But yeah, this is the people that brought up that go over the Gauss stuff, though.
Oh, right. It's about Gauss. My bad.
Yeah,
I was like, hold on.
Yeah, this is gonna because this is how they like if it when you get into well, how did they come up with curved visual space and like what math to use? Well, shout out to the homie Gauss. So anyway, we'll get into that as we continue. But yeah, this is their experiment where they measured that curvature, right? How they substantiated swapping that spherical excess into curved visual space to derive these two field or compression rates for the fields. Anyway, the geometry of visual space is that of the geometry of the visual field is that of the simultaneous presence of the various colored patches. The visual world involves additional depth of dimension. The depth properties are specified by binocular disparities in optical flow and are varied by a bouquet of depth cues. The former involve problems of correspondence simultaneously between the retinal images in case of binocular disparities, successfully in the case of optic flow, and the various prior assumptions no interpretations of the retinal luminance structures. The latter involves such interpretations. Our experiments were performed in a natural environment, open in a field. Oh yeah, okay. So what they're talking about here, they're referencing the previous experiments done for curved visual space, which are the alley experiments. Now the alley experiments are super significant. Get into that here in a minute, but let me show you guys a diagram. So what they have here, imagine you got your boy, the observer here, and this is a dark room, and you have a row of lit candles or lit sources, right? Just some light sources right here, right? And then you have a guy. So the object here is to line these up, is to line up this second row based on this row, just by eyeballing it, because the whole room's dark. You have no reference, just this light source and this light source, and you're just kind of cross-referencing it, moving along the y-axis, right? And then on the distance alley, instead of aligning them long ways, you're aligning them like up and down. So you got an XY axis here in the dark, how they're doing their alignments. And then when they plot that out, if the X and Y axis intersect, that means that we see in curved visual space in Euclidean, because the Euclidean prediction is that the lines would be outside of, let's see, if the geometry is ecliptic, then the parallel lines are outside of the distance. Oh, okay. If the geometry is Euclidean, then the parallel lines in the alley distance are identical. So what that means is they would never intersect. It wouldn't be possible because you would never see it in that. It wouldn't be an option for you to even perceive it that way. So what they discovered, and they started doing this in like around 1856, they started doing like different variations of this. So they knew about this for a long time. They just didn't really, tell people about it or incorporate it very well. But throughout the years, this quote unquote alley experiments have continued, and that's what they're referencing. They're talking about the history of that, and they're saying how their experiment is done in broad daylight. So this is the difference. So like similar kind of reference, but they're doing it in broad daylight to give the full context. that, what they were just talking about here with the depth disparities and the luminous luminous structures and all that. All right. So, our experiments are performed in the natural environment in an open field under bright daylight conditions where everything is in plain sight. No doubt, the observers use large parts of the visual field to estimate the depth of the objects that appear on the horizon. When we mention points or lines, these have to be understood as mere formal abstractions, not reality. Since these were primarily interested in the depth dimensions, we limit our investigation to the horizontal plane through the eye. This plane appears as the visual line in the visual field, so or the so-called horizon of the observer. Of course, we have in mind geometry here. In reality, the horizon need not be specified optically, nor do we confine our research to points. The azimuth is measured along the horizon, and the dimension as a dimension that is measured in the visual field. The depth is the quality of the points of on the horizon. Right. So,
Wow.
would it be fair to say that what they're doing is they're kind of constructing a conceptual azimuthal grid and then taking measurements inside of that to see where the divergence and convergence reaches its minimum and maximums to fit things in your field of view?
Yeah. Sounds about right.
All right. And let me see if I have a quick visual on that. Oh, I do. Nice. The little lad. 1 second.
Just to make sure I understand the alley experiments correctly, the idea there is that those the placement that people perceive that those should go, those lights, they basically overestimate how far inward they should be placed.
Yes.
Okay, that makes sense.
And then the intersection, right? Did we get there yet?
On the other plane.
Right. So, oh god, gotcha.
So yeah,
think
here's
I have-
a. Sorry, go ahead. You're good.
Alley experiment quotes. I think I have 3 or 4 of them from Gleam. Let me get them real quick so we can see where we started.
Oh, nice. Yeah. Hit us up. Oh yeah. Shout out to Gleam. Give the quick history real quick because I didn't know about this, and then I'll give a quick shout out to Skylar
Right.
who presented
Hell
this
yeah.
paper.
So, like, this whole concept of non-Euclidean visual space, as far as I can tell, started with this guy on the internet named Gleam, who's like a music producer and kind of a reggae, I think, a song artist who puts out awesome stuff. And he put these 10 quotes together from various accredited universities, all regarding Euclidean visual space in different ways. Some with an art museum, some with perspective, some with drawing, just all sorts of stuff that generated curiosity in people like Wissit and me who wanted to go look into it. And of course, Alan and everyone who started to think about the differences between what we could perceive and how we could quantify it. And I think that he started us on the path that led us to right here. Shout out to Glee.
But isn't it also crazy, like the fact that like it's super intuitive? Like you literally can't get through a middle school art class without learning about train tracks converging, and that's like kind of the fundamental building block of all of it.
Yep.
Yep. So yeah, and with that said, shout out to Gleam, and then shout out to Skylar, who, when we were all, hearing about this curved visual space situation, he found this paper, and I've read it, several times, and every time I read it, like I learn something more from it, and it turns out that this paper is going to be super pivotal in future arguments moving forward, in relation to how they map the sky to the ground, and then told everyone we live on a curve. So shout out to your boy Skylar who hit us from the, still having a major impact.
The further ether, man. Yeah, hell yeah.
Yep. All right, cool. So let me see here. So we got so that's the visual. So this is what they're talking about conceptually here. The divergence and convergence that goes on in this visual field, and your ability to perceive the physical location of actual objects in this field. Right. All right, we'll continue on. Then let me make sure. Is it back on the? Yes. All right, visually perceived distance, that is depth, usually has been studied under tightly controlled conditions in the laboratory, such as such conditions typically involve extreme stimulus reduction, say few luminous points in the dark, nothing else visible, intensities carefully balanced. So that's what we were just covering with the former alley experiments. Extreme response reduction, say a forced binary choice, the extreme reduction of viewing conditions, say fixed head, probably a bite board, at least a chin rest. So if you ever been to the eye doctors or whatever, when you're doing the eye exam, a bite board would be that, I'm assuming, right? You just put your chin on it. So it's like basically keeping your head in a fixed position and then monitoring how your eyes, move to adjust. See, and probably fixated on instructions. Possible fixation on instructions. So yeah, that was actually something that was mentioned in a couple of these other papers. Is that sometimes the what would you call them? The experimentees, the volunteers or whatever, they would get confused by the instructions, and or there was like a whole thing with that. Um, but yeah, when you find people that are able to follow through without hesitation and all that, it's anyway. So under natural conditions, most of these constraints are violated. Natural conditions are indeed the opposite of stimulus reduction, restricting viewing conditions, and also at odds with a natural setting. In our case, we constrained the location of eye height, but left the observers quite free to make head and eye movements and torso body movements. Even turning on the spot was allowed. We also designed a task that felt much more natural to the observers than a forced binary choice. From the applied perspective, so yeah, these guys really did their due diligence and like looked at the history of alley experiments and like the critiques of them, right? And then now they're applying the future, that knowledge in their experiment. So very cool. So from an applied perspective, such studies under natural conditions are obviously desirable. The scientific value, however, might be less obvious because such studies are less controlled or controllable than laboratory studies. Potential value of the studies in the depth perception in natural environments arises from the likelihood that the observers may change tactics when granted additional freedom in optical structure. Strictly controlled laboratory studies, however, cover only one part of the story. The larger part of the theory, yeah, my YouTube crashed. All right, yo, I'm gonna reset my internet real quick
Dang. Okay.
because it just keeps doing it. I'll be right back.
Damn.
Bummer.
Sorry.
Oh, you're good, man. No, you don't need to apologize.
I thought we were gonna read. Actually, no, this is the one.